You can hand everything back. Let's start. These homeworks, they were due today. This is 4.1 and 4.2. Those are the polynomial homeworks. So we finished talking about polynomials. I moved them back just a day to give you a little bit more time. And I moved this one back some too. I can't adjust them a lot because we're running up against the next week, right, which is the test on a week from today. So they're going to have to be due before the test so that you can be ready for the test. Now, remember, these homeworks that are listed as due on December 3rd, that's just because that's the day of the e-final, which is a Tuesday, but they're really not due until December the 9th, which is our written final exam in class, okay? So even though again, they're scheduled here, you can continue working on those up until December the 9th, that Monday, and there's no penalty, okay, for being late or for working past this due date. So that's just to remind you that the e-final is on December 3rd. If you want to sign up for that, you better do that quickly because I think they've just about run out of slots. So I think today it'll be full if you want to try that. Remember, that's optional, okay? So the announcement for that is on your, somewhere there in the announcements on your homepage in My Math Lab when you log on to do your homework. Remember, the sample test is posted, but I haven't posted the answers yet, so that's in Blackboard. But I'll get around to posting the answers hopefully by Wednesday. So maybe I can, I don't know, let's see. They'll be posted, okay? Eventually, I'm wondering when I'm going to write those. But anyway, so this homework, the 3.3 homework, so that's finished. But so some of you did not work on that. So if you did not work on that 3.3 homework, even though you're not going to earn credit for it, you'll need to go back and still try to work on those problems before the test, okay? So remember, you always have a couple of days past the due date to keep working on assignment and earn partial credit for that. But here we're even past that on this assignment. But you still need to look at that assignment if you didn't work on it prior to the prior to the test next week, test number 3, because that will certainly be on test number 3, okay? So just because you missed it, that's unfortunate for your grade, your homework grade, but you don't want to compound the issue there by not looking at that homework before we take the test, okay? All right, so that's kind of where we are with the sequence of events, right? So this is our last week of lecture, and then next Monday is the test, and then I will not see you again for 2 weeks from the 25th until the 9th, all right? But there are lots of activities going on, final exam reviews and so forth, the e-final, right, in that week that we're not meeting. So again, look at your announcements. Look at your announcements there on your My Math Lab homepage, and I think all the information is there. Let me see if this will switch over to your view. So if you go up to the announcements there, it'll show you when there are review sessions for the final exam. That's the e-final exam announcement, okay, and so forth. All right. Let me see what I put on here. I'm going to check this. Oh yeah, those are just the announcements for the final exam review sessions. Okay. All right. So I'm going to launch right straight into what we were doing last time. So these, as I kind of warned you, right, today and Wednesday, I'm going to be talking a lot. Because there's things I need to introduce for these homeworks. So I'm going to talk for a while here, and then and then we'll have a break, and then I'm going to come back and talk for some more. All right, so so you got to be ready for listening to lecture today, okay, and Wednesday. All right, but the benefit is Wednesday's the last class day, right? So after that is just the test, so it's not too much of this. Okay, we were talking about composition of functions last time. That's a way of taking two functions, or actually just one function. You can compose a function with itself as well. But anyway, but in general, taking two functions and combining them, okay, to produce a third function, a new function. And next time we'll see a little bit better why this composition operation is important to us. But today and last time we were still just practicing, right, what composition is. So let's continue with a little practice here. So here we have two functions. We just got the formula for the functions, not the graphs. And we don't need to make the graphs in this problem to complete this. So we've got the formulas. And remember, this is the way we denote the composition of these two functions. Remember, that's a new function. So when I write f and then this operation, that's not an O, right? That's just a little circle operation. That stands for that composition operation. And then with g, that's just a name for a new function. And in a second here, we'll see what its formula is, okay, what the formula for that new function is, but that's just the name for the function. So like any other function, you can apply that to an input, right? Okay, in this case, I'm going to use nothing special here. I'm just going to use the input 1. So the way you would read this off of that whole expression off of the page, you would say f compose g. So you read that operation as compose. And then, of course, the input here is 1. So you would say f compose g of 1. All right, so we're just, this is something we've done almost since the beginning of the course, right? So I've got a function, I'm going to feed it an input, and I'm just trying to calculate what the matching output is here. All right, now, the way composition works, so this is the important definition to remember, okay? The way the composition operation works is I'm going to first take g of 1, and then when I calculate g of 1, I'm going to use that as input to f, all right? So this is what you want to memorize in order to be able to carry out a composition. F compose g of 1 means f of g of 1. So it's kind of a two-step process here to evaluate. First, calculate g of 1, which you can do easily, right, because you have the formula for g. And then once you get that value, then you're going to use that as input to the function f, right? So first calculate an output from g and then use that as input to the function f, all right? So if you just take that slowly, that's easy to compute, okay? So this kind of problem is kind of a gimme problem on an exam, right? But you do have to remember f compose g of 1 means f of g of 1. All right, let's see what g of 1 is. All right, so I'm just going to take 1, right, and plug it into the formula for g. Let me just write that right inside the parentheses here. So I have 3 minus 2 times 1 squared, right? Okay, because I'm taking the 1, right, and using that as input to the function g. So that's pretty easy. 2 times 1 squared is 2, right? And then you have 3 minus 2. Oh, that turns out to be 1 again. That certainly didn't have to turn out to be 1, the original input, but in this case, it just did. All right. So, so inside the parentheses there we have 1, and now we're going to apply f to 1, right? So now we're just computing f of 1. So now we switch to the formula for f, right? And that also is easy. That's going to be 7 minus 1 divided by 2. Well, that looks like 6 divided by 2. So that's 3, right? So our final answer there is just 3, okay? So for that input f compose g, if you give it an input of 1, you get a matching y value of 3, right? So now, see, notice you can calculate f compose g of an input without really knowing the formula for f composed g. All you have to know is the formulas for the individual functions f and g. But we can also figure out what the formula for f composed g is. All right, and that's just by using x as input. So we have to do a little bit of algebra here and use the variable x as input here in this composition operation. But this is pretty simple algebra, so not that bad. So again, f composed g of x, that's going to mean f of g of x. Well, what's g of x? That just means the formula for g, correct? So you know the formula for g is 3 minus 2 times x squared. So you won't have a number here, right? But you'll just have this formula, g of x, which is 3 minus 2 times x squared. So copy all of that into the parentheses, and now you're going to use that as input to the function f. Okay, this is a little bit trickier, but not too bad, right? To calculate f of this expression, you just take that whole expression, right? And you're going to substitute it for x in the formula for f. So do this carefully now. I'm going to take all of this, right? And I'm going to plug it in to that formula for f wherever I see x. So that's going to look like 7 minus, and then 3 minus 2 times x squared. See, I'm going to substitute all of that in for x. And then divided by 2. Let's see, does this reduce at all? This is 7 minus 3 plus 2x squared over 2. So that looks like 4 plus 2x squared over 2. And yeah, that reduces nicely because 2 divides into both 4 and 2, right? So you would end up here with just 2 plus x squared. That's it. There's the formula for the function f composed g of x. Let's see, does that formula match what we found before? Because a minute ago we found f composed g of 1. That was supposed to be 3. But what do we get when we plug 1 into this formula? Well, remember, when you plug 1 into this formula, you get 1 squared, which is what? Plus 2 is 3. Yeah, matches, you see. Okay, so that formula also gives us f composed g of 1 is going to be 3. All right. So now that you know the formula for this function, right, you don't have to, you wouldn't have to go through this process to compute a matching output, right? You could just use the formula directly. All right. Now, you can also carry out this same composition operation even if you don't have the formulas for f and g. Here's a different question. All right, so suppose we have two functions f and g, but I don't know their formulas, but I do know their graphs. So here's the graph of f. So that's a straight line, right? Okay, and there's the graph of g, nice parabola here, okay? And what it's asking me for is find the y-intercept of something, but not f and g. We can see the y-intercept of f and g. We can read those off easily, right, from the graphs. What we want to find is what's the y-intercept of f composed g, and then likewise, what's the y-intercept of g compose f, okay? So remember, f compose g is a function. It should have a y-intercept, right? And g compose f is a function. It should have a y-intercept. So let's see if we can figure out what those are, because we don't have a graph of this function, right? We don't have a graph of this function, so we can't look at the graph to figure out what the y-intercept is. But we do have a graph of f, and we do have a graph of g by itself. So let's see if we can figure out the y-intercept of f composed g just from the information that we're given. So in general, how do you find the y-intercept of any function? So we've talked about that, right, since the beginning of the class. How do you find the y-intercept of any function? What do you do? No, that's to find the x-intercept. So close, all right. So what do you do there? No, set y equal to 0 will give you the x-intercept. But I want y-intercept. So this is easier, actually. So what do? No, you don't need an equation here. Okay. So set what to 0? Set x equal to 0. Right. You said y equals 0. All right. Okay. Right, yeah. So, no, you said it the second time, too. But anyway, yeah. So you set x to 0, okay? In other words, you're just going to use an input of 0, all right, for the function. So I'm just going to use, I'm just going to calculate f compose g of 0, all right? That will tell me the y-intercept of that function. All right, so this is going to be the y-intercept, because that's how you find the y-intercept for any function. But now we have to figure out, of course, how do we compute f compose g of 0. So what's the secret? F compose g of 0 means what? So you need to learn to recite this, okay? F compose g of 0 means, what did it mean up here? When we were calculating f compose g of 1, that meant what? F of g of 1, right. So f compose g of 0 would be what? F of g of 0, right? F of g of 0, all right? That's the secret that will allow you to evaluate f compose g, okay? All right, well, now you have a two-step process, right? Because you're going to work inside out here. First, calculate g of 0. In other words, you're going to find the y-intercept of the function g, okay? That's g of 0. All right, well, let's see. There's the graph of g. There's x equals 0. What does it look like the matching output is? 3, right, okay. So g of 0 there is 3. So just copy that in, right, where you have g of 0. That's 3, okay. Now, you get just one step left, right? Now we have to calculate f of 3. Well, now we're going to use the graph of f, right? Okay, so there's the graph of f, and hopefully I can see what f of 3 is. If I can't see what f of 3 is, I'm going to get stuck. But can I see what f of 3 is there? Let's see. There's 1, 2, 3. Looks like what? 1. Yeah, there you go. Okay, so f of 3 there is 1. Oh, nice. So apparently, if I were to make a graph of this function, f compose g, its y-intercept would be at 1. We're not going to make the graph of f compose g, but I know that much about it, right? Its y-intercept would be at 1. What about the other one, the other direction? And the reason we need to work in both directions is that when you compose functions in different orders, you usually get a different function. So f compose g and g compose f will not be the same thing, okay? So the way we say that in mathematics is this composition operation is not commutative. You cannot switch the order of the operands, all right? Usually, okay? So let's see what happens here. So let's find the y-intercept of g compose f. All right, so again, there's the little rhyme we want to remember there, right? Well, it's not really a rhyme. But g compose f of 0 is what? G of f of 0, right, okay? So g of f of 0. All right, let's see if we can read these values now off of the graphs of g and f. So what's f of 0? So now we're looking for the y-intercept of 0. Sorry, of f. What does that look like? Here's f. So minus 1? Yeah, okay. So f of 0 is minus 1. And now what's g of minus 1? Can I read that very well? There's minus 1, so that looks like what, 2? Right. So there it is. So see, when you compose the functions in a different order, you get different y-intercepts. So this function, g compose f, and this function, f compose g, not going to be the same function because they have different y-intercepts. Probably look a lot different, actually, besides just the y-intercept. Now, we're going to use a composition shortly here to help us solve equations. So that seems like a very it's hard to understand right immediately how composition can help you solve equations, but we're going to see that, okay? It's actually really important in helping us solve equations, all right? And many of the things that we do in the class, right, come back to solving equations. But another place that composition helps us is in taking a function and trying to write it as the composition of two simpler functions. That's a really important operation in calculus. For those of you who are going on to take calculus, is instead of composing two functions, the way we were doing in the prior examples, instead taking a function and splitting it up as the composition of two simpler functions. So that turns out to be a really useful thing to be able to do in calculus. In fact, we do it a lot in calculus, okay? So let's just get a taste for how that works, all right, in this class. And then again, you'll get to practice this a lot for those of you who are going on to take calculus. So, all right, so let's see. Here, we're going to be given a function in these examples, A, B, and C. We're going to be given a function that's called h, all right? So, just the name I picked for the function. And it's kind of a complicated function in some sense. So, in this first example, h is x plus 3 to the 10th power. Well, that is kind of a complicated function because you're raising that expression x plus 3 to the 10th power, okay? So raising quantities to the 10th power is usually pretty tough, right? Okay. So anyway, here we have that function, h of x is x plus 3 to the 10th power. So what I want to do is see if I can find two simpler functions, so that when I compose these two functions, I'll come up with h, okay? That process is called decomposition. So I'm sort of thinking backwards here. Instead of being given two functions and composing them, I'm given a function and I want to write it as the composition of two simpler functions. All right, so sometimes this requires just a little bit of trial and error, okay? There's no step-by-step process for answering this question. But again, let me remind you what we're trying to find here. I want to be able to take this function h that I'm given, and I want to be able to write it as the composition of two other functions. Hopefully they'll be simpler functions. That's the goal here, okay? Is to make f and g a little bit simpler than the original function. All right. How can we do this here? Usually what you can do is think about one thing you can get to get you started in this process, because it is kind of a trial and error process. One thing you can do is think about what operations are going on in the function, the original function h, right, and try to express those as separate functions. So let's see, in this function, one thing we're doing is raising a quantity to the 10th power, right? We're raising a quantity to the 10th power. So you can write a function that's all it does is raise a quantity to the 10th power. Ooh, what would that function look like? So what's a function what's the formula for a function that it just takes its input and just raises it to the 10th power? How would you write the formula for that? So there's the input. So how do you raise something to the 10th power? Well, yeah, okay. And how do you usually write that? So you multiply it by itself 10 times, right? But how do you normally write that? What? With an exponent, right? Okay. Yeah. So what I'm getting at is one function you can try here is just raising x to the 10th power, okay? See, in this function, h, you're raising this quantity x plus 3 to the 10th power. So let's take a little bit simpler version of that. Let's just raise x to the 10th power, okay? All right, now, again, these are just for us to try, okay? If it doesn't work, when we compose our two functions, we'll try again. All right, what's the other operation that's going on in this formula for h? Yeah, you're taking your input and you're adding 3 to it. So let's write that, just that simple function. What's a simple function that takes its input and adds 3 to it? How would you write that formula? So there's the input. How do you add 3 to your input here? Just write what? X plus 3, right, okay. So let's just try there, x plus 3. So see, see what I tried there again was I just looked at the two operations that were going on in that function, and I just wrote simpler functions with just those two operations. All right, now we have to check this, okay? So these are our hypothetical answers here. So now what we have to do is check these. So we're going to compose these two functions, f and g, and hopefully we'll come up with h, all right? And if that works, then we're done, okay? That's all that we were asked to do here, okay? All right, so let's see. Remember, f composed g of x, that's going to be f of g of x. All right, so what is g of x? What does this show me? What's g of x? It's x plus 3. So now we have f of x plus 3. See, wherever I have g of x, I'm just going to plug in there x plus 3, right? But what's f of x plus 3? What does the function f do? Yeah, that's right. It takes its input and what? Raise it to the 10th power, right? So f of x plus 3 would be x plus 3 raised to the 10th power. So you take all of this and plug it in for x there. Is that what we wanted? Yeah, that's the original formula. See how easy that was? Okay. So see, we met our goal, all right?
So it's always just going to be like pulling apart the original function and then making it...
Yeah, that's the goal here, is to take a complicated function and see if you can pull it apart as the composition of two hopefully simpler functions, okay? The reason that's useful in calculus is in calculus we have to analyze these functions, and if you have a complicated formula, that's hard to do, all right? But sometimes we can catch a break by decomposing the function into simpler functions, and then sometimes it's easier to analyze the simpler pieces than the whole function, okay? All right? Okay, let's try this one. So with this one as a guide, this one is kind of similar, all right? So let's see if y'all can try this. So I've got this function, square root of 2x minus 7, all right? And I want to see if I can write that as the composition of two simpler, somewhat simpler functions, right? So again, I want to write h of x as f compose g of x. So see if you can write down the formulas for f and g that will work. So once you get a formula for f and once you get a formula for g, just try it. Try composing the two and see if it comes out as h. If it does, then that's it. You got it. That's all you needed. So try something, put something down for f and g, even if it's not, even if it doesn't ultimately end up perfect, okay? Because I'm going to ask someone to share, and then we can experiment with it and see if it works, okay? If it works, great. If it doesn't work, then usually you can see how to fix it pretty easily, but you have to start somewhere. Okay, let's try something. So someone want to share what they wrote down for f? What did you write down for f? Just anything. Square root of 2? Okay, well, that is a function, all right, okay, all right, so that definitely counts as a function, all right, so that's a possibility. What type of function is that, by the way? Constant, right, okay, yeah, all right. So Kevin's the only one who's learned constant functions because he always answers that question. So that's a constant function. Yeah, that's a constant function. But that is a function, all right, so that's fine. Well, all right, Arthur, then what about g of x? What else there?
Maybe x minus 7.
Maybe x minus 7, okay. All right, so let's try this. So f composed g of x is f of g of x. So g of x is x minus 7. So that's good, right? G of x is x minus 7. So wherever I see g of x, I'm going to plug in x minus 7. Now I have to compute f of x minus 7. But what, Arthur, what's f of x minus 7? It's just square root of 2, right? Because f is a constant function. Okay, so no matter what you put in for x, you always get square root of 2, okay? So I think making f a constant function wasn't a good choice there, right? Okay, because you're sort of doomed there, right, that your output is always going to be whatever this is, correct? Okay, so I need to get a variable in here. How can I get a variable in there? Square root of x, all right, okay? So let's try that. That's going to be not quite right, but it's a lot closer, all right? So now let's make f square root of x. So we can keep all of this the same until I get to the end, right? So we're still going to keep g as x minus 7. So if I compute f composed g of x, I still get f of x minus 7, and that would be square root of x minus 7, right? Because you would take all of this and plug it in for x in the formula for f. Well, that's close, right? But still not quite right. I need 2x minus 7. So how can I fix that? All right, see, we can fix that by making the g of x 2x minus 7 instead of just x minus 7. Okay? And then let's see, we would have f of 2x minus 7, and then that would be square root of 2x minus 7. Yay, there it is, okay? So there we got it. Let's try one more. This one's a little bit trickier. Maybe, maybe not, okay? So 1 over x squared plus 2x. So can we break that down as the composition of simpler functions? So think about what's happening in this. Think about what's happening in this formula. See if you can break the operations in that formula into two separate functions. Supposed to be x there. All right, let's try something. So just try something. This is like a little bit like factoring. Just try something, and if it works, great. And if it doesn't work, that usually gives you an idea of what will work when you try something. So what should we try here for f of x?
1 over x?
Okay, so Leslie says 1 over x. Because in this formula, right, we have 1 over a quantity, right? Okay, so to make that maybe a little bit easier, let's just try 1 over x, a little bit simpler version of 1 over a quantity, right? And what about for g of x? I guess everything that's left, right? So what's left here in this formula? Yeah, well, x squared plus 2x, right? Okay, so everything that's left. Let's see, does this work now? So do we make that too easy? So f composed g of x is f of g of x. But again, g of x is x squared plus 2x. And now what does f do with its input? It just takes the reciprocal of it, right? Whatever you put into the function f, you get 1 over that, right? So here we're putting x squared plus 2x into the function f. So we're going to get as our output 1 over that. So we get 1 over x squared plus 2x. Ah, that checks nicely, right? Actually, I want to point out, actually, all these examples are really the same. You kind of maybe notice that, right? Okay. The reason these examples are very similar is, see, notice in example A we had we were decomposing a function, and the function was an expression raised to a power, right? The expression was x plus 3, and we were raising that to the 10th power. Actually, that's the same thing as example B. That also is an expression raised to a power, because square root is really a power. What power does square root correspond to? So what exponent gives you square root? No, not square, but square root. What exponent gives you square root? So what exponent is the same as taking square root of a number? What power? 1/2, right, okay. That is 1/2, all right? So a square root of 2x minus 7, we really could have thought of that as 2x minus 7 to the 1/2 power. And then you see that example B and example A are really kind of the same example, right? Here you had a quantity raised to a power, and here, same thing. You have a quantity raised to a power, okay? So they were really very similar examples. And the third example also is very similar, because what exponent takes the reciprocal of a quantity? So how do you write the reciprocal of a quantity as an exponent? Suppose I had 1 over b. How would you write that as an exponent? That's b to what power? 1 over b is the same as what power of b? I'm asking these questions because they're really important questions, all right? I'm not trying to torture you. These are things that are really important for you to know. If you're not going to know them, I don't know, okay? I'm not sure what's going to happen to you. You may end up in a, homeless shelter or something. It happens, all right? So 1 over b is the same as, you're laughing, but what? -1, right, okay, right, okay. So here we had reciprocal, right, okay, but this is the reciprocal of not something as simple as b. This is the reciprocal of x squared plus 2x, right, because you have 1 over x squared plus 2x. So, but we can still write that as a power of x squared plus 2x. 1 over x squared plus 2x is the same as x squared plus 2x to what power? -1 power, right, okay? And then, see, you have an example that's really very similar to this example and the previous example, right? You just have an expression raised to a power, okay? Frequently, when you're decomposing functions, you'll have exactly that pattern, okay? You'll have an expression raised to a power, and if you notice that, then the decomposition becomes pretty easy, all right? Yeah, it would be x to the power of -1, right? 1 over x is x to the -1 power. Yeah, that's right. Well, these things are identical, right? Okay, so you can write them either way. Sometimes it's more convenient to write reciprocal like this. Sometimes it's very convenient to write it like this, okay? All right, so one more definition, and then we'll be through talking about inverses. But we're going to apply inverses shortly. All right. Okay, so if you have two functions, all right, if you have a couple of functions and you compose those functions, so you have to be given the two functions, all right? If you have two functions and you compose them, and it's got to be in either order, but usually one order is enough to check, okay? One direction is enough to check. If you take two functions and you compose them and you just get x, so you just get plain old x when you do the composition, so nothing fancy, you just get plain x, okay, then these two functions have a special relationship to one another. They're said to be inverses of one another, okay? So again, this has to be true though. When you take the functions and you compose them, again, if you just get x, then we say that those two functions are inverses. So we have a special notation for this. It's a little bit confusing because it looks like an exponent, but in this context, it's not an exponent. It's just a superscript notation. Right, so suppose you have two functions that are inverses, then you can write that g of x is, you write f, and then you put a superscript of -1. That means the inverse of the function f. So g is the inverse of the function f. Or you can write that in the other direction. F is also the inverse of the function g. So when you see a function name, and then you see that superscript of -1 written above that, that means the inverse of the original function. So it's not the same function, but it's the inverse. And the relationship that these two functions have to each other is when you compose them, you get x, just plain x. So no, nothing else in the formula, just x. So I summarized that in this this property. Okay. So if you take two functions and you compose them, right, and you get x, that means these functions are inverses of one another. All right. Let's take a couple of functions and let's test to see if they're inverses. Surely they must be, but let's try that. Okay. So here I've got two functions. F of x is 2x plus 5, and then g of x is x minus 5 over 2. Okay, so at first glance, those functions don't seem related to each other, right? Okay, but what we want to check to see is if they're inverses. So if we compose them, will we get just x? Okay, so if that's true, we have to check that because we're not sure yet. But if that's true, then we can write g of x is f to this superscript -1. You read that as f inverse. Or you can write in the other direction as well. You could write f of x is g inverse. Okay, let's check this now. So let's see if this is the case. So again, what I have to do now is compose them, right? To test this, I have to compose them, and I have to come up with x. So if I don't come up with just plain x, then they're not inverses. Of course, lots of functions are not inverses of one another, right? Okay, so it's just a very special pair of functions that are inverses of one another. So that's why we need to test this. All right, so let's see what is f composed g of x. That's f of g of x. What's g of x? That's x minus 5 over 2, right? So x minus 5 over 2. And now I have to take the x minus 5 over 2, right? And I have to plug it into my formula for f. So I get 2 times x minus 5 over 2, and then plus 5, right? See, I'm taking all of this and substituting it where I saw x, right? In the formula for the function f. All right, so let's see, does this reduce nicely now? What happens to the 2's here? Yeah, they cancel, so that's convenient. And then I get x minus 5 plus 5. And, of course, the 5's cancel too, and you end up with just x, which is exactly what we were hoping for. Okay, so yay, it looks like those functions are inverses of one another, okay? Because when we compose them, we get x. Now, technically, you need to do this in both directions because there are exceptional cases, but they're very rare, where you can compose in one order and get x and compose in the other order and not get x, okay? But usually, if you just check in one order, that's sufficient. But let's just try it in the other order. So g of f of x. And again, I'm supposed to get x out of this, right? So now I have g of, what's f of x? That's 2x plus 5, right? And now we're going to take the 2x plus 5 and plug it into the formula for g, where I see x. So that will give me 2x plus 5 minus 5 over 2. Oh, well, that's easy, right? Because the 5's will cancel, and then the 2's will divide out again, and so you get, again, just x. So it does work in both directions, right? F compose g of x is x, and g compose f of x also is x. So definitely those functions are inverses. Well, let's try a harder pair here. Okay, all right. Okay, because I think these functions are also inverses, but this is much less obvious, all right, okay? All right, so 2x plus 3 over x minus 1 and x plus 3 over x minus 2, I think, maybe I did this wrong, okay? I think those two functions are inverses. All right, so let's test this. This time I'm only going to test it in one direction, so let's try f compose g of x. That's going to be hard enough just to test it this way. Right, you can see what's tough about this, right? So this means f of g of x. Well, this step is pretty easy because I just have to take the formula for g of x, right, and put that in here. So I have f of x plus 3 over x minus 2. And now here's where it gets hairy, right, okay? Because now I have to take all of this big fraction and I have to plug it in for x in the formula for f. So that's going to give me a ugly fraction. It's going to give me what's known as a complex fraction because I'm going to have a fraction inside of a fraction. All right, so again, you're taking all of this and you're plugging it in for x here, right, in the formula for f. All right, let's see if we can work through that. So I have 2 times x, but now I'm going to write x plus 3 over x minus 2, right, plus 3. And then that's divided by, now where I see x, I'm going to write x plus 3 over x minus 2. And then don't forget the other minus 2 here. Ooh, that looks terrible, right? Did I forget what? Oh, minus 1. Oh, that would have messed it up, so glad you caught that. So minus 1 there, right? Okay. All right, now let's see if we can, so somehow I have to see if this thing reduces to x. Right now it doesn't look like we have much of a chance, right? Okay, but let's see what happens. All right, so here's how I'm going to simplify this. Let me show you a trick now for simplifying this complex fraction, okay? Again, a complex fraction is what you get when you have fractions inside of larger fractions, okay? And in this case, I can simplify the complex fraction by multiplying by everything by the denominator of these two fractions. Of course, what's the denominator of these two fractions? Just x minus 2, right? So I'm going to multiply everything in the top and the bottom, this, and this, by x minus 2, okay? When you multiply everything by x minus 2, that's really the same as multiplying by 1. So you're not changing the value of the fraction, but you are going to make it look different. All right, so let's see if we can write that out. So I have 2 times x plus 3 times x minus 2, and then I'm going to multiply this by x minus 2, right? That's what I said I was going to do. Plus, you also have to multiply the 3 by x minus 2. So everything's got to get multiplied by x minus 2. If you don't multiply everything by x minus 2, you're changing the value here. Now you're going to multiply x minus 2 in here. So you have x plus 3, x minus 2 times x minus 2. And then don't forget the 1 also is going to get multiplied by x minus 2. All right, now for a moment that looks worse than before, but it's really not going to be worse than before because what nice thing will happen here? What happens right here? Yeah, this is the reason I multiplied by x minus 2, right? The x minus 2's will cancel there, you see, okay? So here, the x minus 2's cancel, and likewise down here, right? The x minus 2's cancel. So see, things are not as bad as they appear. So I have 2 times, this is still here though, x plus 3, and then plus 3 times x minus 2. Well, that's looking better. And in the bottom, I have x plus 3, and then minus this 1 times x minus 2, right? All right, now I think I've got a handle on things. So let's multiply the 2 times the x plus 3. So that would be 2x plus 6, and then the 3 times the x minus 2. That would be plus 3x minus 6. And let's see what's happening in the bottom here. I have x plus 3 minus x plus 2. So the x's in the bottom cancel, but you have 3 plus 2, which is 5. What happens in the top? Well, the 6 and the minus 6 go away, so you just have 2x plus 3x, which is 5x. And then what happens to the 5's? They cancel out. So we end up with, just what we wanted, x, okay? So see, we composed them, and we did get, that took a little bit of work, we did get x. So these functions also are inverses of one another, okay? Because when we compose them, we get x. So if you compose a couple of functions and you do not get x, then they're not going to be inverses. All right, now I'm going to give you a preview of how we're going to use inverses. So this application of inverse is not really useful to us because we have other ways of solving these problems, okay? But eventually we're going to get to problems where the inverses really are our only option. All right, so let's look at this equation. Okay, so what I want to do is solve that equation. Okay, so we know how to solve this equation already. You can multiply both sides by x minus 1, and then it would be pretty easy to solve for x. So we can solve this equation without anything special. We can just use algebra. Okay, but I'm going to show you a different way that we can solve this equation. Because look at that expression that's on the left-hand side, okay? The 2x plus 3 over x minus 1. That reminds me of something here. That is this function, isn't it? From the prior example? Right. That's the same, that expression 2x plus 3 over x minus 1. That's the same as the f of x that I was using in the prior example, okay? So, I can write this equation as follows. 2x plus 3 over x minus 1, that's the same as f of x, right? So I can rewrite this equation as f of x equals 5. Now, at first, that, it's kind of mysterious. Why would we want to rewrite that equation as f of x equals 5? Well, here's why. Because I know what the inverse of this function is, right? What's the inverse of this function? We just saw it in the prior example. What was that inverse? X plus 3 over x minus 2, right? Okay, so I know that the inverse of the function x is x plus 3 over x minus 2. That was the function I was calling g in the prior example. So look, here's what I'm going to do. So I really benefit, okay, I'm catching a break here, because I happen to know already what the inverse of this function is. If I didn't know what the inverse of this function is, then what I'm getting right down wouldn't help me, okay? But since I know the inverse of 2x plus 3 over x minus 1 is this function, here's what I'm going to do. I'm going to apply that function to both sides of this equation, okay? So I'm going to apply the function g to the left-hand side. So I'm going to write down g of f of x. And I'm going to apply the function g to the right-hand side. So I'm going to write down g of 5. Okay? So I'm going to apply the same operation to both sides of the equation. But now, what is g of f of x? Because these functions are inverses. So what's g of f of x? No, I don't want to go through all that work again. I already know what g of f of x is going to come out to be, right? Because these functions are inverses, right? So when you compose two inverses, what happens? You get x, right, okay? The functions cancel each other, all right? The function, you can think of it that way. These functions, g and f, are going to cancel each other on the left-hand side. And we just get x. Cool. So I have x equal, and now I just have to compute what g of 5 is. But that's easy because we have the formula for g. Let's see. G of 5 would be 5 plus 3 over 5 minus 2, right? So we get here 8/3. That's it. There's the solution to that equation. See how fast that was? I just have x is 8/3. That's the solution. So I really didn't have to do any work there at all, okay, to come up with that solution. But I had a little bit of a lucky break, right? Because I knew what the inverse of 2x plus 3 over x minus 1 was, right? So if I hadn't known that, then, this would have been so easy, correct? But since I know what the inverse of this formula is, I can just use that information to solve that equation. Let's try this one. So 2x plus 3 over x minus 1 equal minus 7. Now again, we can solve this algebraically. All right, so we don't need to have knowledge of inverses, okay, to solve this equation. But we're going to arrive at equations where we need knowledge of inverses. All right. So this one we can do algebraically, but we can also solve this with inverse, right? Because what's the inverse of 2x plus 3 over x minus 1? It's this, correct? It's this function. So what I'm going to do is apply this function to both sides of the equation. See, I'm doing the same thing to both sides of the equation, right? Okay, so that should be permissible. I'm going to apply the function g to both sides of the equation. Now, but we already know what's going to happen on the left-hand side. Because, see, this is the function f, and we're applying the function g to it, just like in this previous equation, right? So because these are inverses, what do we get on the left-hand side? X, right, yeah. We're guaranteed to just get x, all right? So you don't have to go through the arithmetic. You're guaranteed this is going to be just x. Now, you do have to calculate g of minus 7, okay? That you have to do, but that's pretty easy because you have the formula for g. So it's minus 7 plus 3 over minus 7 minus 2. That looks like what? Minus 4 over minus 9? Turns out to be 4/9. So, see, just with that one simple step there, we get, there's the solution to the equation, okay? Just x equals 4/9. Okay, well, hold that thought in your head, all right, that we can use inverses to help us solve equations, because shortly here, soon, we're going to arrive at some equations that we're not going to be able to solve without knowledge of inverses, okay? That is the technique that will allow us to solve the equation. So we have lots of techniques for solving equations, right? Factoring, quadratic formula, correct, okay? Well, we're getting ready to learn now another trick in our book here, okay, to help us solve equations. All right. Okay, so this is a good place actually to sort of end at, because we're close to the end here, right? We're going to reach back right to the very beginning of the course, okay? And here we have a table of data, right? So we have this function called f here. And so x is the input, and there's f of x, the output there. That's the y value. And I have just an easy question that you can answer really quickly, okay? Is that function f a linear function?
Yes.
So, but Arthur, how do you check that? Okay, so if you've got a function given as a table, right? So I don't have a formula, I don't have a graph. If I had a formula, I could just look at the formula, right, and tell if it was a linear formula. Or if I had a graph, of course, I can just look at if the graph's a straight line, that's a linear function. But when I'm dealing with a table of inputs and outputs like this one, how do I check if it's a linear function?
Input has exactly one output.
No, that makes it a function.
Oh.
Yeah, okay. So it is a function, yeah. So you're guaranteed it's a function, but is it a linear function? So I'm more specific there. So Kevin, you say no. Why? What's wrong? That's right. Y is not increasing by a steady amount, correct? Okay. So not a linear function. Let's look here. How much in this table, how much is the x increasing by each time? Yeah, that's so that's set up nicely, right? X is always here increasing by 3, right? So since the x is increasing by a steady amount, if this were a linear function, the y would also have to be increasing by a steady amount. Not also 3, correct? But at least a steady amount here, okay? So, well, it's pretty obvious that's not what's happening, right? Let's actually look at what these increases are. Y is increasing. The output is increasing, right? But it's not increasing by a steady amount. So at first it goes up by 1.5 and then 2.25. These are going to get harder and harder, so you're going to help me with this. What's the next one here? Is it 3.75 or something like that? I don't know. 3.375? Okay. And finally, what's the last one? 5.065? 625? Okay. All right. So I want to compute those exactly for a purpose here. But to answer this question, the answer is already obvious, right? Okay. For the reason Kevin said, right? X is increasing by a steady amount, but the Y is not changing by a steady amount, right? Okay. So to have a linear function, the Y would have to change by a steady amount. So the answer here is no. Okay, so why bring up this example at this late date? Because this table is a little bit more complicated than it looks. All right. Let's calculate here. Instead of just calculating the change in the outputs that you do through subtraction, okay? So instead of just calculating the change in the outputs, let's calculate percent change. All right. So do y'all remember how to calculate percent change? Okay. Yeah, so it's something like that, Amber. Can you remember that? Yeah, you're right. Yeah, it's I usually said it as last minus first, okay, divided by first, right, and then times 100 to turn it into a percentage, correct? Okay. All right. So what I want you to do here is calculate the percent changes here. So I want each percent change instead of this is the total change. Let's calculate percent change. This percent change, this percent change, this percent change, and this percent change. So that gives us 4% changes, all right, to calculate, okay? All right. Can y'all calculate those for me? All right. So try that. Try calculating the percent changes, not the total change there, but the percent changes in each one of these outputs, okay? So it's last minus first, right? Last percent change there. Amber said the formula. So it's last minus first over first, right? And then times 100%. So let's go quickly because we want to take a break here. Okay, so compute fast there. So I don't want you to go, this is not the first and this one is the last. Do it each pair. So percent change here, percent change here, percent change here, percent change there. Okay. So we've already done last minus first, right? Okay. So you just have to divide that by the first one and then convert that to a percentage for me. So here, just take the 1.5 divided by 3 because that's the first, right? This is already last minus first. And then write that down as a percentage. All right, what are we getting? What's this one? 50%. Okay, what's this one? 50%. Right. 2.25 is half of 4.5, right? So that's 50%. What's this one? 50%, okay? And what's this last one? Is it also 50%? Okay. So there is something steady in this table, okay, right? Okay. There is something steady in this table. It's not that the outputs are changing by a steady amount, okay, but the outputs instead are changing by a steady percentage, all right, are changing by a steady percentage. This type of function is also very important in mathematics, like linear function is. This type of function is called an exponential function, all right, exponential. Exponential functions are functions where you have a steady percent change in the output instead of a steady change in the output, okay, like we do for linear functions. All right, so we want to talk now about exponential functions, okay, and look at some applications of the so-called exponential functions. All right, so let's stop there and take a few minutes, and then we're going to go back and then we're going to come back and talk more about exponential functions. But the key thing about exponential functions have a steady percent change in the output, okay, rather than like linear functions where you have a steady change in the output, okay. Okay, functions that again I mentioned, there are functions that have this steady percent change property as opposed to steady change property. These are called exponential functions. Let's take a look at what the formulas for exponential functions look like, because they have very nice, easy formulas. And some of their other properties are easy too, okay, to understand. So the formula for an exponential function, again, just has this very simple format to it. You just have a constant here. This is a constant times, and then you have a base, which also is a constant, so that's just a number. And then your input there is, notice that's in the exponent of the base. That's why these are called exponential functions. The x there ends up in the exponent of this base. So see a very simple, easy formula, kind of easy like linear functions, right? Okay, except just slightly different. And again, now this value b, that's the base of the exponent, that's called the base of the exponential function. It's also called, however, the growth factor for the exponential function. So you can hear both of those terms used interchangeably. And this constant that's multiplied, but notice this constant is not raised to the x power. This constant is called the initial value for the exponential function. It's really the same as the Y-intercept, okay? But there's a reason why we call it initial value. You'll see in applications of exponential functions how this terminology initial value comes about. But it's really the same as Y-intercept. Now, I want to show you something about the growth factor, though. So this is important because this is what really allows you to write down formulas for exponential functions. It's usually easier to write down the formula for an exponential function even than for a linear function. The growth factor, or the base, you can always find that by taking 1 plus whatever the steady percent change is. In your exponential function. Remember, exponential function, you always have steady percent change in the output, right? Okay, so just take just take 1 and add into that the percent change. But now this has to be the percent change though when x increases by 1. Okay, so it's got to be the percent change when x increases by 1. Kind of like slope, right, is the change when in linear functions, right? When x increases by 1, you find the growth factor for an exponential function by taking 1 plus, again, the percent change, but it has to be when x increases by 1. So let me write that in there because I didn't put that down before, but that's important. Okay. And usually that's easy to determine from the situation what this percent change is. Let's look at just other easy properties of exponential functions. The domain is really nice. The domain is all real numbers. So just like for linear functions, their domain is all real numbers. So for exponential function, the domain will be all real numbers unless, again, there's some sort of other reason why the domain is restricted. But just from the formula, you can have the domain all real numbers. The range, however, though, is not all real numbers. So for exponential functions, the range is only going to be from 0 to infinity, not including 0. Notice 0 is not included, okay? So exponential functions do not have 0 in their range. And then also, I mentioned before, right, the Y-intercept is going to be this value C, right, okay? But in the context of exponential functions, the Y-intercept is often called the initial value. All right, let's take an easy example of an exponential function, see if we can write down the formula for it, okay? So suppose we're in this lucky situation. We've graduated and we take this job, and our initial salary is $50,000 a year, but this is a union job, okay? And in the union contract, we are required to get a 5% cost of living raise each year, okay? So we're going to get a 5% raise each year. And so we want to let S be the salary that we're going to make after X elapsed years, all right? So S will be our salary, and X will be the elapsed number of years right after we start. First question is very obvious there. That's asking, is S a function of X? In other words, if you know in this job, if you know the elapsed number of years after you've started, will you know what your salary is? Sure, right, okay, right, okay, definitely, right, okay. That's because you know what your initial salary is, correct, right, and you know what your cost of living raise is going to be each year, right, okay, it's going to be 5%. So, you know, based on that information, of course, if you know the lapse number of years, you can calculate what the salary, of course, is going to be, right? So this is true, right? The salary is a function of the elapsed number of years. But we can go beyond that because we actually know what sort of function this is, right? What type of function is f? It's got to be exponential, right? That's kind of obvious, right? Obviously, this must be an exponential function. Why is s an exponential function? So if we were asked to explain why s is an exponential function, what could we say? Right, it has to do with that percent increase, right? So what would be the proper way of saying why s is an exponential function? Because what? The salary, right, is the salary, which initially is 50,000, is for exponential functions. You want that output to be changing by what? A steady what? A steady percentage for exponential function, right? Okay. Well, is the salary changing by a steady percentage whenever x goes up by 1? Yes, right. Whenever the year changes, s is changing by a steady percentage. What's that obvious steady change? 5%, right, okay? Yeah, so see the outputs from this function, the salary, are, in this case, increasing, right, by a steady percentage every time 1 year goes by, right, each elapsed year. So, so we have an exponential function. If the salary was changing by a steady amount, if you were getting, for instance, a $5,000 raise every year, right, okay, that would be a linear function. All right, but because your salary is changing by a steady percentage, this is an exponential function instead. You may wonder, which is better? Do I want a constant raise or do I want a constant percent raise? And the answer is, you do not want a constant raise, Joshua. You would prefer to have a steady percent raise, okay? That's because in the long run, you will do better, all right, okay, with a percentage change, okay? We'll see that when we look at a graph of this. Okay, so yes, not only is s a function, it's an exponential function. Let's see if we can write down the formula then for that exponential function. So remember, I said the formula always looks like this, right? Just have very simple formula for exponential functions. You've got that initial value, correct, right? Okay, and then your base, and then just to x power. So what's our initial value for 50,000, right? That's the initial salary. That's the same, by the way, as the Y-intercept. And you know the Y-intercept here is 50,000 because 50,000 is the salary when x is 0, right? Okay. When you first start the job, when the elapsed number of years is 0, your salary is 50,000. So our initial value must be 50,000. Now, what's our base here? Remember, you have to take 1 and then add on the percent change, right, okay? By the way, exponential functions can decrease, so you can have a steady percent decrease. In that case, you would subtract off the percent change, okay? Well, what's our percent change here? 5%. Do not write that as a percentage, though. Write that as a decimal. So what's 5% written as a decimal? Exactly, 0.05, okay? And then just to the x power. So you have 50,000 and times 1.05 to the x power, okay? That's it. Just easy to formula to write down, just like linear functions, right? Also easy formulas to write down. Let's take a look at the graph of this. Let's take a look at the graph of this exponential function. See if I can get this thing to wake up here. There it is. Okay, so there's the graph. I started the graph just at 0 because elapsed time cannot be negative, right? Okay, but you could extend the graph over here to the left as well, and see there's your graph. See, not a straight line, okay? Not a straight line there. And what's important, maybe not the only thing, but one of the things that's important about exponential functions graphs is you go further to the right here, what do you notice happens to the graph? It gets steeper, okay? That graph is getting steeper as you move further to the right there, the graph is getting steeper and steeper. That means, Joshua, that as time goes by, what's happening to your rays every year? It's getting bigger. That's right, okay? Your rays is getting bigger, you see, okay? That's the advantage of a steady percent change in the rays rather than a steady amount, okay? As time goes by, the rays is getting more and more, okay? All right. Let's take a look at some other exponential functions. Let's just try evaluating one to start with here, though, okay? So sometimes they're not so easy to evaluate. They're not as easy to evaluate by hand as linear functions because the input is, again, in this exponent, right? Okay, so let's look at this exponential function. This would be an unusual one to encounter in practice, but this is good as an example. So we have 2 times 9 raised to the x power. So in this exponential function, what's the initial value? Not negative 2, just 2, right, okay? So the initial value is 2, and what's the growth factor here, or the base? 9, right, okay? That's a pretty big base for an exponential function. Usually they're not that large, okay, all right? But it can be any size, all right, at all. So the base there is 9. Let's try evaluating f of minus 2. What does that turn out to be? So, you can plug that easily into the formula. So you get 2 times 9 to the minus 2 power, and now we're back to this problem we were discussing earlier. How do we raise 9 to the minus 2 power? What does it mean to raise 9 to the minus 2 power? That doesn't mean minus 9. What does that mean? What do negative exponents? How do you simplify negative exponents? What is that telling you to do? Reciprocal, right, okay? So you really have 9 in the denominator, but it's 9 squared in the denominator, okay? So 9 to the minus 2 is same as 1 over 9 squared. The 2 is going to stay in the top, though, so you have, because that's not being raised to the minus 2 power. So you just have 2 over 9 squared. Well, that's easy to calculate. That's 81. So f of minus 2 is 2 over 81. Notice it's not 0, okay? Again, exponential functions, you cannot have an output of 0. The range does not include 0. So you don't get x-intercepts of exponential functions. Exponential functions don't cross the x-axis. What about f to the minus 1/2 power? So that's 2 times 9 to the minus 1/2 power. Wow, can we evaluate 9 to the minus 1/2 power? First, take care of the minus sign. What does the minus sign do? Reciprocal. So you have 2 over 9 to the 1/2 power, and now we have to remember what 9 to the 1/2 power means. Is we talked about this earlier. What does 1/2 power mean? Square root. So this is 2 over square root of 9. 2/3. So you see, we can evaluate that one by hand. What about f of 0? That one we know what that has to turn out to be. Because remember, when you use 0 as input, you're going to get the y-intercept always for any function. But what did we say the y-intercept was? 2. Yeah, it's the same as the initial value. Okay, so f of 0 has to end up to be 2. You can see, by the way, why that's the case, because this is 2 times 9 to the 0th power, and what do you get when you raise a number to the 0th power? 1. So you just get 2 there, right? This one should be easy. What's just plain old f of 2? Well, that's 2 times 9 squared. Well, that's not hard. That's 2 times 81, right? 9 squared is 81. So you get 162. Ooh, wow. That function's growing really fast. Notice at minus 2, it was this tiny little number, 2 over 81. So it's very close to 0 at minus 2. But by the time you get up to 2, on the right here, it's already jumped way up to 162. That function is really increasing very rapidly. Okay, already up at 162. Let's look at some of their graphs here. So these are pretty straightforward exponential functions. Just have different initial values and different bases. So what's the initial value here for this one in A? 2, right, okay. So that has a y-intercept of 2. The growth factor is 1.5. So what's the steady percent change in this exponential function? Yeah, 0.5 as a percentage, though. So not 5%, 0.5. How much is 0.5 as a percent? 50%, right. So this has a percent change of 50%. That's growing by 50%. The output is growing by 50% every time x increases by 1. So that's a lot, okay? So percent change there of 50. It's actually the steady percent change is 50%. So if we graph this one, let me see if I can find the graph here. There's the graph. All right. Wow. See that exponential function again. See, notice the domain can be all real numbers, so it's going to extend all the way across the x-axis, right? But it doesn't touch the x-axis, so no x-intercepts there. Even far on the left here, it gets really close to the x-axis, but it won't touch the x-axis. But notice what's happening on the right, because that steady percent change is so high. This thing is really increasing rapidly, so it's really shooting off very rapidly to positive infinity. Not a straight line, right? Obviously, correct. Okay, but not a complicated curve, right? But it really gets very steep over on the right-hand side. It looks like, in fact, it's almost going straight up. Okay, it's increasing so rapidly. See, for this one, we have an unusual base here. The initial value is easy. That's 3. So the y-intercept is 3. But the base here is e, okay? That is a number, all right? That's an irrational number. It plays an important role in calculus. And kind of like pi plays an important role in geometry, this number e plays an important role in calculus. It's about 2.71828, but it's a non-terminating, non-repeating decimal. So the decimal expansion keeps going on forever, and it doesn't repeat ever, actually. All right, so you get a long and totally unpredictable decimal expansion here for this number e, but it's a little bit less than 3. This is a very common base for exponential functions, e. Okay.
What would that be? Because it's such a random number.
Yeah, it's not really a random number. It's just an irrational number. So the decimal expansion, again, doesn't repeat. All right. That same thing happens for pi. Pi has an infinite decimal expansion, but it doesn't repeat. Okay. Square root of 2 has the same property. It has an infinite decimal expansion, doesn't repeat. Okay, so it makes it seem like it's kind of random, but it actually has several ways you can draw a geometric definition of the number e. Okay, just like you can for pi. All right. So if you graph this one, that also is a pretty big That also is a pretty big base there. Okay. See how rapidly that escalates, right? Okay. Ooh, that's growing really very quickly. All right. Notice that the red curve here, this one is growing faster than the blue curve because the base here is E. That's 2.718. That's a lot more than the base here, which is just 1.5. So 1.5, that base exponential function is already increasing pretty rapidly, but the one with base E is going to be increasing even more rapidly because the steady percent change is bigger for this base. Let's look at this one where we have a base less than 1. You're going to get a very similar curve, but different. So here, the initial value is 4, but the base is 1/2. So what steady percent change does that correspond to? Negative, right, okay. That's going to be a negative 50% change, okay, minus 50%. So you have a steady change of a negative percentage. So this function is decreasing from left to right, okay, instead of increasing from left to right. The output is falling by 50% each time x increases by 1. So when you graph this, you're going to get the same curve, but let me turn these off. You're going to get the same curve, but instead of increasing from left to right, you get a curve that's decreasing from left to right, okay? Because here the outputs are falling by 50% every time x goes up by 1. Okay, I want to just introduce you to an example here of one place where exponential functions are applied, okay? But I don't think we'll get a chance to answer the questions here, okay? But they're pretty straight. They're pretty, well, no, okay. No, we'll make them easy to answer. All right, so here's one famous example of exponential functions. The radioactive element radium, but this same applies to every radioactive substance. Radium is just the first known radioactive substance, okay? So that was, that's an element, so it's on the periodic table. It was isolated by Marie Curie in 1898, okay? And this is, again, the first known radioactive substance. So radioactive substances decay, right? They dissipate over time, okay? The reason they dissipate over time is that their nuclei are not stable, okay? And so the nuclei are dissolving, and you don't want to be around the radioactive substances usually because what's happening is when you're close to them, you're going to get bombarded by subatomic particles because the nuclei of these atoms are decaying, right? They're falling apart. So the subatomic particles will be bombarding you if you're standing close to the radioactive substance. Well, you cannot feel that, of course, because the particles are subatomic, but they will interact with your genes, Montel, okay, in your cells, and that they will cause cancer eventually, okay? If you stay around that long enough, okay? All right, so, but these substances usually decay, well, it depends on the substance. Some radioactive substances decay very quickly and some decay very slowly, but radium decays very slowly. We're going to measure in this function, we're going to measure elapsed time in centuries, okay? That's how slow radium decays, all right? So the T here is elapsed time in centuries. The initial amount of the radioactive radium is going to be 1 gram. So we're working with a very small sample of radium here. The reason I chose 1 gram is because that's how much radium Marie Curie was able to isolate. Was 1 gram of radium. It took her 10 years, okay, to do that. Okay, it was very painstaking work in her laboratory to isolate 1 gram of radium. Well, fortunately, notice that the growth factor here is very close to 1, okay? So that means the radium is not decaying very quickly, all right? Not decaying very quickly, but it is decaying, okay? As all radioactive substances do. So that was good for Marie Curie, because if she was busy trying to isolate the radium, right, but it took her a decade to isolate 1 gram. Of course, if it had been decaying rapidly, she, it would have been hard for her to isolate it, right? Because it would have disappeared as soon as she was able to extract it, correct? Okay, but instead it decays very slowly. All right, so notice it's an exponential function that governs the decay of the radium, and it's actually exponential functions that decay, that control the decay of all radioactive substances like radium. Okay, all right, so we're going to take a look at this this exponential function next time, and see if we can answer some questions about what happens to that 1 gram sample of radium. Okay.